Hello, welcome to Biological Physical Chemistry. Chemistry course is 3453. My name is Susan Schroeder, and I'll be your professor for this course. We'll be studying the fundamental physical chemistry concepts that help explain biological phenomena. It's a one-semester course, and I'm looking forward to our time together. We'll be asking questions like, how much energy does it take for a small RNA therapeutic to bind to the RNA in HIV? How much energy does it take to unwind bacteriophage? Bacteriophage DNA is the genome of viruses that infect bacteria. We'll ask how much energy is in a hydrogen bond in RNA enzymes, and some of these enzymes occur in pathogens like Pneumocystis carinii or Candida albicans. We'll ask how magnetic resonance imaging technology can be used to diagnose and detect Parkinson's sooner and in vivo. So we'll ask what the structure of DNA is and how Watson, Crick, Wilkinson, and Franklin figured it all out. We'll ask how water can help a protein fold. We'll also ask how a peptide drug can bind HIV RNA to inhibit its replication. We'll ask how a flu virus can package all 8 of its genome segments in one virus particle. So if these questions interest you, then you'll enjoy this course. We'll study the physical chemistry concepts that underlie these biological phenomena. So let's start by imagining photons in sunlight traveling all the way across the solar system from the sun through the Earth's atmosphere, and then think about what might happen next. Those photons could land on a leaf and begin a series of chemical reactions called photosynthesis to convert that energy from light energy to chemical energy. Those photons could also land on a solar panel, which would then convert that energy to electrical energy. Or maybe those photons land on a magnifying glass that focuses that light and generates heat. If it happens to focus on a pile of brush, then it can cause enough heat to generate a combustion reaction and cause a fire. On the other hand, those photons may land on a bucket of water, and that water will heat up and eventually it will evaporate, and that's one type of phase change. Those photons could also land on human skin, and if you're out long enough, hopefully that human skin is protected by sunscreen that protects the UV components of that light from damaging the DNA and causing cancer. Those photons of light may also land on a helium balloon. Imagine if you took a helium balloon from your party in a nice, well-air conditioned room and then brought it outside and left it outside on a hot, sunny day. That balloon would start to expand. The volume would increase and do pressure-volume work. All of these examples demonstrate the first law of thermodynamics, that energy is constantly changing, but energy is conserved. Do you remember the first law of thermodynamics from general chemistry? How about the ideal gas law? We'll revisit many of the topics in general chemistry, but delve deeper to better understand how and why these phenomena occur. General chemistry, organic chemistry, physics, and calculus are required for this course. The first homework that's due this Friday will review concepts from these courses that you will need to review, and then we will build on them as we learn more about physical chemistry and how to use physical chemistry to solve questions in biology. We'll start with the first law of thermodynamics. There are 3 videos that follow this. The first question we'll ask is how much force is necessary to unwind bacteriophage DNA. The next video focuses on how much work is done by a typical person every day, every time they exhale air. The third video reviews some fundamental calculus concepts. I look forward to meeting you in person in the next class.